Spatial statistics has a fundamental problem that nobody's talking about. Standard methods cannot handle the massive datasets modern research requires. In this video, I'll show you how the ExaGeoStatCPP software solves this problem. ExaGeoStatCPP is a high-performance computing software that enables large-scale spatial analysis that were previously impossible to do. The challenge isn't just that traditional methods are slow, it's that they fundamentally break down as the size of the dataset grows. The computational complexity scales cubically, meaning if you increase your data points by 10 times, your computation time increases by 1,000 times. This isn't just a matter of waiting longer, it is a mathematical barrier that prevents certain large-scale spatial analysis entirely. What you're seeing here is the cubic scaling problem in spatial statistics. This graph plots the computation time in seconds on the y-axis against the dataset size on the x-axis on logarithmic scales. This graph shows how brutally computation time scales in spatial statistics. When we increase our dataset just tenfold, from 100 to 1,000 points, the computation time explodes, from less than a second to nearly 2 minutes. Push that to 10,000 points, now we're waiting for almost 3 hours. We couldn't even complete the computation for 20,000 points. It would theoretically take days. But computation time is only part of the problem. Even if you're willing to wait, memory constraints create an absolute barrier that no amount of patience can overcome. Looking at this graph of memory scaling in spatial statistics, with just 1,000 spatial points, we need about 10 megabytes of memory. At 10,000 points, we are approaching 1,000 megabytes. The red lines show the common memory limits. A standard laptop has 8 gigabytes, a desktop or server has 32 gigabytes, and a high-end memory server has typically 128 gigabytes. Even with a high-end server, we cannot analyze 25,000 points because we would need more RAM than the system has available. There is no workaround. Once you exceed available memory, the analysis simply cannot run. These computational limits and memory constraints aren't just theoretical problems. They are crippling our ability to analyze modern spatial datasets. Think about it. A single satellite pass generates millions of observations. Global weather station networks produce continuous streams of climate and environmental data. Climate modeling involves hundreds of three-dimensional variables across the globe, like temperature, pressure, wind patterns, and ocean currents. Forecasting disasters requires modeling of terrain data, vegetation patterns, and weather conditions simultaneously, and often in real time. We are collecting more spatial data than ever before, and the need for spatial statistics continues to grow. Spatial modeling is crucial to understand climate change and to predict disasters. However, our ability to analyze this type of data is hitting a computational wall. This is why we need a software like ExaGeoStatCPP that can handle the true scale of modern spatial modeling. ExaGeoStatCPP addresses these challenges through high-performance computing techniques and approximation methods that maintain statistical rigor while dramatically reducing computational requirements. What this means is that spatial analysis that would take days or months can be completed in hours or even minutes. ExaGeoStatCPP is built to use all the computing power you have available, from multiple processor cores to graphics cards and even entire computing clusters if you have access to them. The big advantage is speed. What might take days using regular tools can be done in minutes or even seconds. This isn't just more convenient. It means you can tackle problems that were completely out of reach before. The market is flooded with powerful new GPUs and AI accelerator chips from vendors like NVIDIA, AMD, and Intel. ExaGeoStatCPP is engineered to harness these advancements, automatically detecting whatever hardware you have and optimizing workloads without user intervention. Researchers can simply plug in the latest cards and immediately apply the computational firepower to previously impossible spatial problems. As chip performance doubles every generation, ExaGeoStatCPP users ride this wave of innovation, tackling larger datasets and more complex models without changing a line of code. The software future-proofs your spatial modeling capabilities, ensuring that your research scales with hardware evolution. It's very easy to get started with ExaGeoStatCPP. Just go to this website bit.ly/ExaGeoStatCPP and it will take you to this Google Colab notebook where you can try out the software. You have two options for working with this notebook. First, if you want to save your work and come back to it later, you'll need to create your own copy. You won't be able to run codes or save any changes on the original version. Second, if you want to experiment quickly without saving anything, you can use the playground mode. Simply go to File and select Open in playground mode. This lets you run the code immediately without saving any changes. There are several steps that you need to do in order to be able to install and use the ExaGeoStatCPP software in this Google Colab session. This is the outline of the steps. There is nothing for you to do except to go through each of the steps and click the small play button on the left side of each code cell. Once you click this button, the code will start running and you will see a small spinning icon that shows it's working. Below the cell, you will see the output as packages are being installed. This might take a few minutes, but you don't need to do anything while it's running. Just wait until you see a checkmark appear. This means that the code has finished running. And then go to the next step. The entire installation process takes about 20 minutes. Once it's done, you're ready to start using the software. In this example, we'll use ExaGeoStatCPP through its R package interface. Since we're using Google Colab, which normally runs with Python codes, we need to start our R code blocks with the symbol %%R. It's like telling the notebook to switch to R mode. One of the most important functions in ExaGeoStatCPP is simulate_data. This allows you to create spatial data. To use the function simulate_data, you need to tell it exactly what kind of spatial data you want to create. In dimension, you can put 3D if you want a three-dimensional spatial data. In n cores, you can put 4 if that's the number of cores you have available. In n GPUs, you can also put the number of GPUs you have. The problem size is the number of locations where you want to generate some observations. DTS stands for dense tile size. This parameter controls how matrices and vectors are divided into blocks for parallel or distributed computing. This parameter is one of the most important parameters you have to tune when you are working with very large data sets and you want to speed up your computations. LTS stands for low tile size. This is the tile size you use when you want to perform tiled linear algebra operations. Computation can either be exact or some approximation methods that ExaGeoStatCPP supports. Kernel indicates the covariance function model. ExaGeoStatCPP supports a lot of spatial, spacetime, multivariate, Gaussian, and non-Gaussian covariance function models. Initial theta is just a vector of parameter values to the kernel or covariance model. The P and Q values define how to distribute the workload across your hardware resources. Later on, when you get more familiar with the software, you can tune these parameters to optimize the performance on your machine. These two lines are where the real action happens. First, we're setting up our hardware configuration. The new hardware command tells ExaGeoStatCPP exactly what computing resources it can use. In this case, 4 CPU cores, but no GPUs. Then, we use simulate_data to generate our spatial data. We feed it all the parameters we just set up. When this runs, it will create a complete spatial dataset with known covariance properties, perfect for testing spatial analysis methods. Let's try increasing the number of locations to 400 and see how the values look like on a map. You can remove these other codes for now. These are the codes that you are going to use if you have a specific data set on file for your location where you want to simulate some data. We'll try them out in another example. Let's look at what we get from simulate_data. After it runs, it gives us several things. First, it gives us the values at each location. Those values are stored in the variable m. It also gives us information about the location, such as the positions in the x-axis. You can think of it as the longitude. The positions in the y-axis, you can think of it as the latitude. And the positions in the z-axis, you can think of it as the altitude. So for each point in our space, we know exactly where it is and what value it has. Now that we have our simulated data, we can visualize it. We can use the quilt.plot function from the fields package. It is a great way to see spatial patterns in our data. Think of it like a heat map, where different colors show how values change across your spatial grid. Here's how our simulated data looks like when mapped out. The colors show us where values are high and low, and you can see how they change across space. These patterns come from the spatial covariance structure we set up in our simulation. When you do this with real data, you might see similar patterns representing things like temperature changes, pollution levels, or any other spatial phenomenon you're studying. Let's see how ExaGeoStat handles a much larger dataset. Here we're simulating 22,500 locations. That's the kind of scale where traditional methods would fail. We've set our tile size to 560 and we're timing how long it takes to run. We're also using the same parameters as before, just scaled up significantly. The code measures the execution time down to the second, showing us exactly how long it takes with our current hardware setup using 4 CPU cores. This gives us a real sense of ExaGeoStatCPP's performance with larger datasets. The code finished generating our 22,500 locations in 173 seconds or about 3 minutes using just 4 CPU cores. That's pretty impressive, but here's the thing, we can make it even faster. ExaGeoStatCPP is built to use multiple cores and GPUs, so if you have more computing power available, say 16 cores or a couple of GPUs, you could dramatically speed this up. The software automatically adapts to whatever hardware you give it. Let's visualize this larger dataset. Since we're now working with 22,500 locations instead of just 400, we get a much more detailed map. The higher resolution reveals finer spatial patterns that we couldn't see before. This is what we mean by large-scale spatial analysis. We can capture subtle variations that would be lost with fewer data points. ExaGeoStatCPP has many other powerful features that we haven't covered yet, like parameter estimation, spatial prediction, and advanced approximation methods. We'll explore these capabilities in upcoming videos. But for now, you have seen how it handles the fundamental problem of large-scale spatial data generation. Thanks for watching and see you in the next video.